Hello, this is Maraj Patel here, and today we're going to be finishing up the rotation unit, and we're going to be talking about statics and kinematics. So, statics. So what is static? And so static means that something is stable. And I'm sure most of you have heard of static electricity. Static electricity is caused by a charge that's stationary on an object. And so, when you bring a piece of metal to it, it'll actually move. So that's what static actually means. Static means stable or like stationary. So in rotation, if there's a force in a moment arm or pretty much a fulcrum, it will cause a rotation. Like, for example, the easiest example to imagine is a seesaw. For example, you have a force, which is a person, and you have a fulcrum, and this is the moment arm here, and this causes a rotation. And notice that the girl pushes down the seesaw because it wants to rotate to the counterclockwise, but this apple doesn't have enough force to counteract the rotation. So a force in a fulcrum will cause a rotation. But if it's static, it will not be rotating and will be stable. So if it was static like this scenario, even though this guy weighs so much more than this lady here, because of the way they're placed, this is static and not rotating. So statics is all about balance of forces. And so in physics, we're gonna use statics and equal and balance torques. So since torque is Fr sine theta, we can use this to balance the torques on both sides of the fulcrum and have it balanced. So like if we have the seesaw here, we can use this equation to balance out the torque. So this is a force, the man's weight, the lady's weight's a force, the r, the radius, is the length from the person to the fulcrum, or the center of mass, which is pretty much right in the center of a person to the fulcrum. So that's r, and then sine of theta is the angle between. And because it's 90 degrees, pretty much it's always going to be 90 degrees. You just multiply the force or the weight of the person times the distance away from the fulcrum, and you will get the torque. So it's kind of simple. You don't really need to use the sine part. You just multiply the force, or the pretty much the mass of the person, and the distance away from the fulcrum. So let's do a simple problem to show you what this is all about. A 50 kilogram mass is 1 meter away from the center of a homogeneous board. How far does the student have to place the 25 kilogram mass on the other side so that they balance equally? So to do this problem, I'd first suggest to draw an image of what you're exactly doing. So here you have a seesaw, and you have a 50 kilogram mass right here. It's 1 meter away from the center, or the fulcrum here, which happens to be in the center. Then we have a 25 kilogram on the other side, and we don't know how far we have to place it. But this is stable, we know that. So how far do we have to place it? That's the question. So what are the forces? So there's two forces basically, which are the masses of the blocks. So because the earth or whatever planet they're on is pulling them down, this is causing a rotation for the board. Since they are perpendicular to the moment arm, the torque is the distance from the center times the force of the weight, which is mg. So basically, I talked about this. Since the angle is 90 degrees, we just multiply the weight, or mass times gravity, times the radius, or how far they're from the fulcrum. So I'm going to set the torques, pretty much the sum of the torques is equal to 0 because it's statics. So statics have no motion, so the torques is 0. So I'm going to call the 25 box positive because it wants to make uh, the seesaw rotate to the right, and I like to call right positive. So so the force of the 25 kilogram is going to be positive, and this is its radius or this its distance. And then the force of the 50 kilogram box, which is on the other side, and its distance, which is 1, which we are given that. So I called this negative because it wants to twist it to the left. Okay? So the torque of the 25 kg minus the torque of the 51 is 0. So that's what that just means. So now if I substitute, because mass or weight is mass times gravity, and gravity is 10, so 25 kilograms times 10 times its radius is the torque, because force times moment arm. And then the 50 kilogram, same thing, multiply by 10, because on Earth gravity is 10, and then multiply by its moment arm, which is 1 meter. So if I do this, but if I just divide every term by 10, I just get the simpler form here. So I just divided everything by 10 uh, because both terms have a 10 and you can divide 0 by anything. So that this cleaned it up, and so I have 25 times the moment arm minus 50 equals 0. So if I move 50 to the other side and divide by 25, notice that the radius is 2 meters. So if you remember, the other mass was 50 and it was 1 meter away. But this mass, since it's half, we have to double the distance it's away so it generates the same torque. So the the force or the mass and the torque are like inverse. So like if we have a heavy mass that's one half okay, so basically if we have a bigger mass and it's very close, and we put a lighter mass on the board, it has to be farther away than the bigger masses because the torques have to be equal. And since the torque is just mass and distance, if the mass is greater and we're trying to balance it with the lower mass, we have to put it farther away. So, so you'll get to notice that there's a pattern here, and it sort of makes sense. Uh, if you have a heavy person and on a seesaw, and to balance them, you would want to, and if you're lighter, you would want to sit farther out on the opposite side, depending on the ratio of your weight to the other weight. So let's just say, for example, if there was a 100 kilogram mass on a seesaw, and you are only 33 kilograms, you would have to sit uh, 3 times as far as the other masses. And same thing, if you're one half the mass, you have to sit twice as much, just like in this case. And if you both weigh the same, then you have to sit the same distance away from the fulcrum. So it's all ratio. The distance is all about the ratio of the masses. So let's try a harder problem. And this problem is a more difficult problem. And so there's a 5-meter homogeneous board, and 2 meters of it are hanging over the building. The board weighs 100 kilograms total, and Bob, who is 100 kilograms, is walking on the board over the edge. How far can he walk over the edge before the board falls? And important thing is that homogeneous just means that the board is similar throughout, pretty much the same throughout. So that means that it's an ideal board where every single particle weighs the same. So every single piece of the board weighs the same. In reality, boards like a wooden board, it's from a tree. So trees aren't exactly perfectly homogeneous, but because there's certain parts that are more dense, so some of the weight is not ideally distributed. But since I said it's homogeneous, we can assume every single part of the board is exactly the same. So that's what that means. So let's go back to the problem. So I drew a picture here. So this is supposed to represent the building, and this side is the part with all the offices and stuff. So there's a board, 3 meters is within the building, 2 meters is hanging over. Bob, who is 100 kilograms, is walking over the edge, and we want to know how far he can walk before he falls to his doom. So we use a similar strategy, but it's just going to get a little more complicated. So it's static, so we have to know the sum of the torques is equal to 0. So the torque on the left must equal the torque on the right. That is a fact, because we know that they add up to 0. So since the fulcrum this time is not in the center, we must consider the weight of the board on each side also. On the other problem, since we had the fulcrum in the center of the seesaw, we did not care about the board on one side or the other because it was equal. But on this one, the board's weights do not cancel out on both sides, so we have to put that in our equation here. But the good news is it's all the same principle, but we just have to consider its weight. So since the board is 100 kilograms total and there's 5 meters of it, so 100 divided by 5 is 20. So each meter of the board weighs 20 kilograms. So that's basically just the density sort of per length of the board. So basically, I'm going to do the same thing as I did before. The everything on the right is going to be positive, everything on the left is going to be negative. So the weight of Bob, so the force of Bob times how far he is away from the fulcrum, times the weight of the right side times the distance it's away, minus the weight of the left side times its distance away from the fulcrum equals 0. So this is basically the statement above, but expanded. So sum of the torques is 0, so this is exactly what we mean. So, this is where it gets a little complicated. How do you measure how far away the right side is from the center or from the fulcrum if it's touching it? And that's when you use the center of mass. So, so we got these distances for the right side and left side, 1.5 and 1, by the center of mass of each side. And okay, so force of Bob, since he weighs 100 kilograms, we just multiply that by 10 to get his weight. So 100 times 10. The right side, since it's 2 meters long and each meter is 20 kilograms, it must be 40 kilograms. So if we multiply that by 10, we get its weight. And then since it's 2 meters long, the center of mass is in the middle. And since the middle of the side is 1 meter away from the fulcrum, that's how we got this distance. The left side is 60 kilograms because it's 3 meters. Each meter is 20 kilograms, so the board is so it's 60. And then we multiply by 10 because that's gravity, and then the radius or the distance away is 1.5 because 3 meters we divide it in half because the center of mass of a rectangle is just in the center. So it's in the center of the 3 meters, so that's 1.5 away. So this is our statement. So that's pretty much the hardest part. And so here's the picture I drew. Because the 3 meters is on this side, imagine this as a separate board. The center of mass of this will be right in the center, which is 1.5 meters away from the fulcrum here. With the 2 kilogram side, it's only 1 meter because that's the middle of the 2 kilogram side. And then we have Bob's torque, which is this blue arrow here. So, since all of them are masses, you can just go ahead and divide by 10. So now that you know that if you're dealing with only masses, you do not have to include the 10. But it's important that you do it if you're talking about forces and masses. since because these are all masses, we just divide everything by 10 because they're all multiplied by 10, and we just get this simple statement here. And we just do a little algebra. So if we add each side by 90 and subtract 40, we get 50 on the other side equals 100R. Divide each side by 100, and we get Bob gets to walk 1.5 meters before the torque is unbalanced. Then it wouldn't be statics, it would be dynamics. So now we're going to briefly talk about rotational kinematics, which is just a review, basically. Kinematics or rotational kinematics is no different than one-dimensional kinematics. And basically, the variables are just substituted by these, which are angular acceleration, alpha. Then there's omega sub I, which is initial angular velocity, omega sub f, final angular velocity. Theta, which is the angle or the displacement. Just like x in kinematics, theta replaces x. So it's the angle of displacement. And t is for time. And so the formulas are, just like in kinematics, there's average acceleration. So final velocity minus initial velocity over time. So angular final velocity minus initial angular velocity equals acceleration. Then there's 2 for theta. This is the average velocity equation. So initial angular velocity plus final angular velocity divided by 2 times t equals displacement. And then angle of displacement, this is Galileo's formula, equals initial velocity, angular velocity times time, plus 1/2 angular acceleration times time squared. And then the last one is the energy formula, again, which looks very similar to the kinematics one, which is final velocity squared equals angular initial velocity squared plus 2 times angular acceleration times the displacement. And notice the translational versions look exactly like the rotational versions, except they're replaced with these weird variables. But it's exactly the same. So let's just do a simple problem. A disk is rotating at 3 radians per second. It speeds up to 7 radians per second in 6 radians. How fast did it accelerate? Okay, so step 1 is list your variables. So you have initial angular velocity, which is 3 radians per second, initial final angular velocity, which is 7, and the displacement was 3 radians. And then we have the unknown here, which is the acceleration, which is, by the way, is in radians per second squared, so it's always important to have your units. So I just wrote it right there so you know. So what is the equation that has all 4 of these variables? And so that's when you have to ask yourself, what is the equation you want to use? So I picked the energy equation. So this equation has all the variables except for time because we don't need time. And so this will be very helpful to solve this problem. So now we have to manipulate the equation and plug in. So that's the last step. So we want to solve for angular acceleration. So let's move everything to the other side. First I would subtract by initial angular velocity squared. Then I would divide each side by 2 in theta, like that. And we would get angular acceleration. So if we plug in all those numbers, 7 was the final velocity, 3 was the initial, and then the displacement, was 6. So we put that on the bottom, and we just divide everything, square it, subtract, then divide. So we get 38 divided by 12 equals angular acceleration, and it's 3.17 radians per second squared. Always remember to put your units. So I forgot to mention this earlier, but it's important you know the right-hand rule when you're talking about physics and torque. So the right-hand rule is a way to determine whether torque is positive or negative. And basically, you just use your right hand. So stick out your right hand like you're giving a handshake. So just do it right now. And this represents the moment arm. Then curl your fingers in the direction of the force. So just curl it towards you. So curl it to your left. So you stick out your right hand, curl it to the left, and then point up your thumb, and that represents the direction of the torque. So if it's up and to the right, it's positive. If it's down or to the left, then it's negative. So let's just say you stick out your right hand, bend your hand, curl your hands to your right, so your hand will be upside down. Then this torque is negative because your thumb's pointing down. But if you stick your right hand out, curl it to the left, your thumb will be up, so that's a positive force. Then let's just say you stick out your right hand and twist it to the left, so twist it left so it's horizontal. Curl your hands down, that will be negative because it's to the left. Stick your hand out, curl it, face it so it's palm up, curl it upward, that's positive because it's pointing to the right. So just practice your right hand rule. But if you if you're already comfortable with naming forces, whatever negative or positive, as long as you are consistent, you will solve the problems correctly. So just like how in kinematics I like to call up positive, down negative, you can be a little different and call up negative and down positive. You will still solve it correctly as long as you put everything in the same consistent sign. So remember, always keep your signs consistent and you will solve every problem correctly. But you just have to tell the person who's grading your teacher, just tell them or what you want to call what. So if you want to call up positive, down negative, that's like the standard. But if you're feeling kind of different, you can call the down positive, up negative. You just have to indicate that somewhere, and you will get the answer correctly. So thank you for watching my physics video today. So today we talked about rotational motion, finished it up. We talked about the right hand rule, kinematics, and statics. And so tune to the next video or next group to learn about waves. So we're going to be learning about light and sound waves primarily. Please, if you enjoyed this video, spread the word and like this video down below. Please email me any questions and comments at mpatelbuccaneer@gmail.com. I would gladly answer any of your questions. So for chemistry tutorials, if you're taking chemistry, please visit my website, buccaneerchemistry.weebly.com. And thank you for watching. And be sure to practice your materials. And make up your own problems. Just do the problems on this video over and over again until you get them, and you will surely understand physics. And thank you for watching, and I hope to see you next time.